Yeah. Is there a
Hello, everyone. Our next speaker is Adam Burgess, and he will talk about from weak to strong coupling, scalable quantum master equation framework for energy transport systems. Adam, the floor is yours.
Thank you, Esther, and thank you for organizing this wonderful event. Uh, as Esther said, I'll be discussing the topic of modeling quantum transport in large networks. So what is the kind of motivation for the work that we have done at Heriot-Watt? We're thinking of these large light harvesting networks. So here we have a chromatophore from a purple bacteria, Rhodobacter spheroides. And it's an interesting system because it's built up of lots of individual subunits. So we have these LH2 rings and these LH1 sort of figure of eight systems. And photons that are incident on this chromatophore typically will land on these LH2s, and via rapid energy transfer, excitations move towards the reaction centers of these LH1 systems. So we zoom into these substructures, we can see that the substructures themselves, so here we have an LH1 and some of these outer LH2 rings. These substructures are also built up of individual substructures. So here we have bacteria chlorophyll, which is a light-absorbing molecule. So we kind of think of these light harvesting networks as kind of just a network of all of these individual molecular systems. So we're theoretical physicists at Heriot-Watt, so we try to come up with kind of reductive modeling for understanding these systems. And I think Philip already mentioned this earlier today. We think of these bacteria chlorophyll, and we perform a simple reduction where we think of the orbitals of these systems. So we have here the HOMO and the LUMOs, and the energy differences generated by these orbitals allow us to construct a simple two-level Hamiltonian that has the energy difference encapsulated between these HOMO and LUMO states. Another particularly relevant aspect of these molecular orbitals are the transition dipole moments. And these transition dipole moments effectively encode how these systems interact with light, the photon field. And this is given by sort of a overlap between these excited states over some spatial degree of freedom. And this is the so-called dipole approximation. So if we return back to this large system, because we are thinking of very low light levels, we're typically in any meaningful time scale, there's only one photon in our network, and therefore only one excitation in the network also. So this enables us to construct a single excitation manifold Hamiltonian, where we have these sort of HOMO and LUMO energies encapsulated in this epsilon term, which tells us the energies of each of the sites in our network. And then we have some coupling terms, which is typically a Coulombic coupling between the sites in the network. And within this dipole approximation, it will just be the dipole-dipole coupling between these molecules. So why are we actually interested in a quantum mechanical approach to understanding energy transport? Well, when we account for these Coulombic couplings, these energy eigenstates of this system become very delocalized. So here, if we think of just two sites in a network, we can find when the sites are entirely degenerate, the Coulomb coupling creates these fully delocalized eigenstates, where an excitation is, a single excitation is spread across two molecules. And depending on the phase of the state, we can get some very interesting optical properties that can be leading to super or subradiant nature. And that effectively manifests in summing up these individual dipoles given by these phase relationships between these states. And because these dipoles, I said, induce this dipole-dipole coupling, they can also have quite important impact on energy transport in these systems. So I wanted to give you a sort of prototypical perfect case example where you have almost perfect quantum coherence across these sites. So if we think of a sort of canonical donor-acceptor system, where we have one excitation localized on one donor, passing energy to an acceptor at a rate gamma, then if we're allowed to have these delocalized eigenstates, it turns out that we can double the strength of this transfer rate. And in fact, this is a process that's known as supertransfer, because as we increase the number of systems, we can get a maximal n-fold enhancement of this transfer. But as I mentioned, we have this sort of reductive modeling of our system where we just think of these electronic states. But now we can add in all of the complex nature of these environments, all of the geometrical degrees of freedom, all of the vibrational fluctuations from the proteins, the solvents, and even the breathing modes of these systems. Here I've shown a spectral density, which is sort of just a frequency resolved version of all of these fluctuations from the environment for each individual site in these networks. And these can be generated by these breathing modes that I mentioned before, which leads to these highly peaked structures in these spectral densities. And this highly peaked spectrum effectively means that these vibrational degrees of freedom very strongly couple to our system. And because these breathing modes are necessarily localized where these molecules are, this will lead to strong localization in our network. And this localization ultimately is what's going to break down the superradiance in these networks, because the vibrations are strongly coupled and lead to an effective localization of these eigenstates. And these are modeled by these harmonic oscillators. So we can imagine that we effectively couple quantum springs to our system that have the same frequency response as the actual frequency response of these molecules. So now we've sort of conjured our model system, which is these electronic degrees of freedom and these coupled vibrational degrees of freedom. How do we actually go about modeling these systems? Well, in principle, we have a continuum of vibrational degrees of freedom. So the Hilbert space that we're dealing with, effectively the number of degrees of freedom is almost infinite. So we need to use the open quantum systems paradigm, where effectively we think of partitioning our total system into a system of interest and a sort of complement, which we'll call this environment. And typically this partitioning will happen between our electronic degrees of freedom and our vibrational degrees of freedom. And once we have this partitioning, there are many schemes in which you can use to effectively account for the induced effects of this environment on the system without actually caring about what the environment itself is doing. The sort of most generic approach that captures all of these degrees of freedom, though, is just as complicated as solving the entire problem. So we have to leverage some approximate approaches to try and capture these effects in a reasonable way. We had some talks on how HEOM has been used and how DAMF can be used to solve these types of problems, but they're very computationally expensive. So I'm going to introduce a couple of perturbative approaches. Here I have kind of two axes, which is going to go from weak to strong vibrational coupling, and in the opposite direction, weak to strong Coulombic couplings. So in this strong Coulombic coupling or weak vibrational coupling, we can utilize this Bloch-Redfield equation of motion. And this is a very common tool used in this field. But as I mentioned before, this spectral density told us that, in fact, these vibrational degrees of freedom are very strongly coupled to our system. And as such, a weak coupling theory is not going to be appropriate for capturing these effects. At the other extreme, we have the so-called polaronic Redfield theory. And this is where we effectively think of the joint vibrational degrees of freedom and the electronic degrees of freedom as a quasi-particle called a polaron. And this polaron, because it has these vibrations built in, is naturally going to be more localized than the electronic excitations we saw previously. But again, I said we have this strongly coupled spectral density, so maybe polaronic theory is a more relevant theory. But because we have this multi-scale nature of these light harvesting networks, you might think that very proximal dipoles or molecules within this network will see strong electronic coupling, whereas spatially disparate molecules will feel very strong vibrational coupling. So there's sort of a disparity between which regime you want to be in. So ideally, we'd have a theory that works in a sort of intermediate coupling regime. And this is where this so-called variational polaron transformation approach comes in. And the idea here is that we sort of generate an ansatz of what an appropriate quasi-particle to make between these vibrational degrees of freedom and the electronic degrees of freedom is. And then we optimize this ansatz such that it minimizes the free energy in the system. And the rationale for doing this is that effectively, when we think of this partition we have now in this open quantum systems paradigm, the partition between this quasi-particle polaron and the residual environment is going to be minimized when we perform this free energy minimization. And just to show that this actually works, the idea has been explored in small systems. So this is a two-level system, and it was shown that here in black is the variational polaron work. In green is numerically exact data. In blue is weak coupling, and in red is the polaronic theory. And what we find is across a large range of different parameter regimes, the variational approach is capable of capturing most of the effects of these numerically exact approaches with much less complexity. Though it sounds like it's kind of a golden bullet, but it has its drawbacks. And the problem is, if you were keen, you might have seen in the previous slide, that effectively we're displacing every individual vibrational degree of freedom and performing this optimization on every vibrational degree of freedom for every site in the network. So this makes it incredibly expensive to perform this optimization. And that's before you even do any dynamics, which previously limited this approach to relatively small networks. But we thought if we kind of go back to our chromatophore system and take two spatially disparate molecules in this network, is it obvious that their optimization should have any meaningful effect on one another? So following this idea through, we utilized a partitioned optimization approach, where we think about each site in these networks optimization only being performed with the knowledge of the most strongly coupled other dipoles in that network. And if you follow through the mathematics of this, what you find is that the error you introduce versus the global optimization turns out to be second order in couplings from your partition to other to everything outside of your partition, which is actually quite easy to minimize in these types of networks, where you have these spatial geometries that you can actually now leverage because of this natural geometric structure of these networks. So this enabled us to take this variational approach, which was limited to at most 7 sites. And now we're able to expand it to thousands of sites for these optimizations. So here I have a rod-like system in these purple bacteria, as well as a sort of toy model helical system. And the idea now is that we just increase the size of our partitions, and we see how these variational parameters change. And if they change only on an order of 10 to the minus 5, we say, well, we've got converged variational parameters. So as we add more and more of these dipoles into each of these partitions, we find that we get convergence quite rapidly compared to what is here. We have over 5,000 sites, but we can get convergence to an order of 10 to the minus 3 with only, say, 20 or so sites in this partition. So this then now has enabled us to study dynamics in these types of systems. So we kind of look at this canonical LH2 complex system, which has this highly peaked spectral density that you may have recognized from Nicola's talk for the FMO. It has a sort of similar highly peaked structure here. And we're able to propagate the dynamics. So these dashed lines are weak coupling theory. And here we have an excitation starting in the B800 outer ring. So we have these B800 molecules on the outer ring of this LH2 and the B850 on the inner ring. and we watch as excitations kind of go from the outer ring to the inner ring. And we can see that the weak coupling theory greatly overestimates the coupling strength. And that's because these weak coupling theories typically have almost an extensive scaling. So as coupling strengths increase, you almost get a linear scaling of your transition rates. But in fact, because we have these polaron formations, when we strongly couple to vibrations, it actually becomes harder to transfer energy between these sites. And because of the sort of efficiency of this network, because now the method has almost the complexity of a Lindblad-Master equation, whilst accounting for strong coupling to vibrational degrees of freedom, we can actually scan through adding different vibrational modes into the dynamics of our system and see how different modes impact transport. So here I'm showing how long it takes for 80% of the population to go from the outer ring to the inner ring as we add these modes that are color-coded as up here. And what you find is that as we start to add these low frequency modes, it takes longer and longer for transport to occur. And that's because these low frequency modes effectively act as a source of static noise in these systems. Then as we start to add more on-frequency vibrational degrees of freedom, we get a drop in the transfer time. And this is because we're able to leverage phonon-assisted hoppings in our network, because these phonons are now resonant with the transitions between our energy eigenstates. And then as we add these higher frequency modes, transport slows down again. And that's because these high frequency modes effectively just act to renormalize the coupling rates in our system and just slows everything down as they have like an almost adiabatic profile on our system. We're then also able to study larger networks. So here we just conjured a toy model of a sort of a chain system, a spiral system that has an energy bias along its gradient. And we're able to capture dynamics along this gradient for up to nanosecond timescales. And within this framework, something that's quite nice. So here we're calculating the coherence length, which is a metric for how delocalized is this Gibbs state over different sites in this network. And what you find is a second order phase transition as we increase the coupling between the vibrational degrees of freedom and the electronic degrees of freedom, where eventually you just perform full polarons in your network, which is to say that effectively the quasi-particles are no longer these electronic excitons, but these highly localized polarons. Another thing I wanted to discuss was that now that we can do these optimizations in large networks, we can ask, say, this rod-like system in these sulfur bacteria. Here I'm plotting this coherence length again, which is a sort of metric of how many sites on is my Gibbs state delocalized over as I add more and more rings, right? And we see this nice growth of the coherence length as I add more and more rings. But this is within the weak coupling approach. If we now account for these vibrational degrees of freedom, we find that this growth is both stunted and ultimately ends up at a much lower level, showing that these polarons do, in fact, localize our excitations within these networks, which will ultimately, this is sort of a proxy for this superradiant terms in our Hamiltonians, and it shows that accounting for polarons also will suppress the superradiance in these networks. So I wanted to finish with a few conclusions. Now, by utilizing this variational framework that's scalable to huge networks, we're able to have a physically motivated understanding of energy transport in these networks that accounts for strong vibrational degrees of freedom, as well as strong electronic degrees of freedom. And this was achieved by utilizing this partitioned approach to the powerful variational polaron-master equation. And we're aiming to generate now efficient representations of the actual master equation itself beyond just this optimization step to extend this to studying energy transport in phycobilosome, as well as in organic photovoltaic systems. And I'd like to finish with a couple of acknowledgements of Professor Kara Gauger, the leader of the quantum theory team at Heriot-Watt, and a collaborator, Nick Warren. And we have the preprint on the archive at the moment. Thank you for your time.
Questions?